unfortunately, I cannot reach India and Belai, but I'm very pleased to give this presentation entitled Some Research Advances on the Radical Copolymerization of Fluorinated Monomers with Functional Monomers and Application. Of course, I will give some background on organic chemistry in order to design some fluorinated monomers and to see how they can be copolymerized. So for the people who didn't attend my previous presentation, I come from France. I am in the south of France, especially in a city called Montpellier, which is about 10 kilometers from the seaside, and this is the city center, which is very nice, and many students are here. So just to mention that in order to speak about fluoropolymers, we need obviously to have some information on the monomers. And as you know, PTFE, called also Teflon or Neoflon, according to the companies, can be produced from TFE, which is tetrafluoroethylene. You have to pay attention that this gas cannot be carried and is dangerous because in presence of oxygen and pressure, it can explode. Then you have other monomers, just like chlorofluoroethylene, CTFE, on which you have done a lot of work on that, which has an application for film forming properties, especially the PCTFE, with a TG of 50 degrees compared to that of PTFE, and a melting temperature which is lower than that of PTFE, because PTFE is very well organized in the conformation and leads to a very high crystallinity. The presence of a chlorine, of course, makes a kind of kink which does not allow a high crystallinity. I mean, the melting point is high, but it's okay. Then you have VDF, which is also a gas. So just to mention that all these monomers, TFE, CTFE, VDF, and vanillin fluoride are gases. They have to be carried out in autoclave experiments, vessel. And PVDF is a very nice polymer with a TG minus 40 melting point lower than that of PCTFE. Its range according to the defects of chaining, because it's not a symmetrical polymer in which you have some change of organization. Let's say you can have CH2CF2, but also you can have F2CF2 or CH2CH2, some defects of chaining. And then polyvanillin fluoride, which has a TG of 40 Celsius, and a melting point of 200 and a degradation of 240. So just keep in mind, this monomer can be polymerized or even copolymerized under radical polymerization with persulfate or peroxide in different process, can be in solution, in emulsion, in suspension. They have a high crystallinity rate and they have low solubility in organic solvent. PVDF can be soluble in DMF, DMSO, and NP. And they have a difficulty of cross-linking. Cross-linking means you want to enhance the properties. So you need an autoclave. So I mentioned that this is the pyramid of polymers in which you have in the bottom, and the most produced are commodity polymers, then you have intermediate polymers, and then you have high-performance polymers. And the fluoropolymers, just like PTFE and PVDF and other fluoropolymers, are in this top size, in which the production range is the smallest also. So I come back to this slide, which is interesting because Teflon was accidentally produced by the use of TFE, which was generated by the pyrolysis of CFC22 in order to make difluorocarbene. This difluorocarbene recombined in order to make some TFE, called Teflon because it was in DuPont. And they observed a white powder which was insoluble in all solvents and very high thermal stability. So PTFE has the highest production volume, followed by PVDF, FEP, and some estimation trends show that more and more PVDF will be produced because of the binders for lithium-ion batteries. The initiation, the polymerization of a monomer is radical polymerization is the result of three main steps: initiation, propagation, and termination. And in which the propagation, of course, is going to lead some ratio selective but in radical polymerization, it's not really ratio selective. This means that you can have some head-to-head additions, and usually the recombination of two macroradicals occurs for the termination step, while the disprobation does not occur. And of course, all the reactions are conducted in autoclave. I just mentioned that for those who were not in the previous presentation, but we had a manometer to check the pressure. We have a valve to introduce and to release the gas. We have a rupture disc for security, and the mantle, which is assisted by a controller in order to heat the temperature, and also a spinning band in order to shake all the reaction, to stir the reaction. So just one example is how to make a CF3 radical. This idea was very important because we had a lot of requirements, especially to measure the molecular weight. And we don't know what is molecular weight. And one trick could be to know by, for instance, NMR. If you have the N group which is known, how you can access this molecular weight. And indeed, from the literature, we know that the CF3 radical can be generated by different systems. So this can be made by telomerization, so we'll speak that later. By this IFO, this paraffin, this Paris carbonate, this thio sulfur compound, and also the CF3Br, but this doesn't exist anymore. This was published at least 30 years ago. And then also more recently, Azande in University of Connecticut used this kind of compound in which when you generate some visible light, you are going to release some CF3 CO2, which loses CO2, yielding a CF3 radical, the UV. And we recently used what is called the Langlois reactant, which is this trifluorinated sodium, in which with an oxidant, it was possible to release some CF3. And even in the last 10 years, we have been working on what is called perfluorinated hindrete compound, which also led, but I'm not going to speak today about that. So the idea was to use a system which enables to release some CF3 in order to have a CF3 N group and then to have a polymeric chain, so that the CF3 N group by NMR was possible to give an information about the molecular weight. So we did homopolymerization of EDF, but also copolymerization of EDF and HFP, and even terpolymerization of EDF, HFP, and perfluoromethyl vinyl ether. Under these conditions, we need an oxidant in order to oxidize that to release the CF3 radical. So this oxidant, just like persulfate or from the literature, this tertiary hydroxy radical enables to release this unstable intermediate, which led to the CF3 radical able to react into VDF. This was very well known, and we published that 2 years ago. If you look at the NMR, for us, this is very important because we did so many models with a CF3, knowing that when you have a CF3 adjacent to a CH2 of VDF, you have a signal at -61. When we make an expansion of that, we see the quintet of that. And from the different characteristic signals, this is, for instance, the HFP from here, you have also a lot of signals here, but this one is linked to VDF. Another one is linked to VDF adjacent to HFP. Another one is linked to VDF adjacent to PNDE. This is linked to the presence of a CF in perfluoromethyl vinyl ether, and the CF3 here is -53 here. So you have a very nice resolution of your spectrum. The CF here of HFP is -180, and from the different integrals, it's possible to calculate the molecular weight. So we found, so of course we have to be very careful because we might have some error, about 5 to 10% error, but in this case we have a molecular weight of about 50,000. And when you look at the thermal stability of the copolymers bearing a CF3 N group, this is here, so very stable, compared to that prepared in the presence of a persulfate in which you have a sulfate, sorry. You can see that you have a decomposition here because you have a depolymerization starting from the N group, in this case, at a lower temperature, while the presence of CF3 does not allow to have this depolymerization. So this is what is called the unzipping depolymerization system. So what was interesting, we did in water, we work in water, we didn't use any surfactant, we had a very good thermal stability compared to conventional polymerization of monomer in presence of persulfate. So now PVDF is very important because this polymer has many applications. I mentioned the binders for lithium-ion batteries. So this is also for electroactive polymers, especially piezoelectricity. It can be used for membrane filtration, desalination of water, for pure water transportation, for energy. So you mean for batteries, for instance, or as a backsheet of photovoltaics. Chemical process, wiring cables, polymer additives, oil and gas, and protective coating. A lot of facade and buildings have been coated of PVDF for UV protection and many applications. So you can see that PVDF has, of course, is nowadays less produced than PTFE. But it is estimated that in the 10 years there will be a growing production of this polymer, and maybe it can be the production can be higher than that of PTFE, which could be a very good surprise. So PTFE can be prepared from HFC22. VDF can be prepared from CFC 142b. I don't insist on these figures, but this is the number of carbon, the number of fluorine -2, -1, and so, and what is important is from this derivative, by dehydrochlorination, it's possible to make VDF and then to make some PVDF or copolymers of VDF with, as I mentioned before, HFP, PMV, etc. So just to mention that the consumption of the PVDF is very important. From 22 to 27, the estimation is going to increase to double, more than double in China, more than double in Japan, because Korea company is producing that. In Europe, we have Arkema and Solvay, which are producing and is planned to double in 5 years. So as you can see, the production of PVDF will increase a lot. And this may be the way why it's estimated to be higher than PTFE. So for the sustainable energy transition is driven by PVDF because gigafactories of lithium-ion batteries are produced, and we have 4 gigafactories in France. There are several hundreds in China. I think there are also gigafactories in India. And again, the estimation for PVDF in lithium-ion battery, you see, is increasing a lot, okay, compared to that of photovoltaic, which is slightly increasing. It's the proper way. And for architectural system, it's a little bit steady with a very slow increase. So the batteries from 26 to 44, almost double in 5 years. So now the issue on PVDF is there is no function. And indeed, if you want really to get some insight on the properties and the applications, it's necessary to have a function. So either you modify VDF or PVDF, or directly you find out a suitable copolymer able to copolymerize with VDF. But keep in mind that you want, of course, to keep the backbone of VDF. So this means that you need a high amount of VDF. And one example, this is very patent writing. X, Y, and Z can be a proton, fluorine, and CF3. You can have a spacer or not. NG can be a functional group, just like sulfonic acid or phosphonic acid. ammonium or bromine. So these are for membranes. The bromine or tritosylene, acido for cross-linking, or even by grafting for click chemistry, for instance. You can also think about PVDF is hydrophobic. It's not very hydrophobic, but for membrane filtration, water desalination, it's good to have some hydrophilic channels. And by using some carboxylic acid or PEG substitutes, you can induce some hydrophilicity, or even in the case of PEG, you can have some lithium conductivity because you have coordination of the lithium by the oxygen of the PEG. So the idea is if you are able to manage this group in your PVDF, okay, you can have a function, give some information on proton exchange membrane fuse cell, or even cross-linking to get high performance sealant or rings, directly copolymers with a high amount of VDF, of course, solar cells, we put some phthalocyanine, for instance, or even lithium-ion batteries in case of PEG or cyclocarbonate. In addition, what is very important is, according to the content of VDF and the copolymer, you can have amorphous or crystalline compound. And indeed, when you look at the structure of the copolymers based on VDF and HFP, hexafluoropropylene, so the presence of a CF3 side group is going to reduce the crystallinity so that you can have amorphous compound. And this can be used as elastomers. In the case of less than, let's say, 20%, you have semicrystalline copolymers. And of course, these are the different names of trade names of companies for which these copolymers have been produced. So you can have, you see, you have here some flexible PVDF by different companies, and here some amorphous copolymers for Technofront, for instance, or Fluorel or Vital. So this is very interesting. We list here some references we published in this area, and I want to thank all my co-workers who have been very efficient, and Professor Banerjee, who came in my group, did a lot of reaction in this time. Thank you again. When you look at that, it's interesting on the academic point of view to investigate the reactivity ratio. And indeed, when you have two comonomers, you can have some VDF reacting onto VDF. So this is called homopropagation. Or you have what is called a cross propagation. So this macroradical is able to react onto M, and the ratio of K11 to K12, which has a rate of reaction, are defined as the reactivity ratio. On the other hand, if the macroradical is terminated by M, monomer, it can react either onto VDF by cross propagation or by homopropagation. And in this case, the reactivity ratio of the monomer M is K22 versus K21. And indeed, when I look at the literature, if you consider the diagram of composition, which means that this is the mole fraction of monomer A, for instance, VDF, in the copolymer versus the mole fraction monomer A in the feed that you put in the autoclave, if you are 50-50 in the autoclave, the copolymer doesn't have necessarily 50-50 because you have a different reactivity of both comonomers. So for instance, if you take some HFP, pentafluoropropylene, this kind of monomer, or perfluoroalkyl vinyl ether, which are not homopolymerizable, you are going to get this kind of behavior. Let's say if you start from 50-50, you will have about 90 percent of VDF because you have a kind of PVDF, then 1 unit of HFP, then a PVDF, 1 unit of HFP. So in contrast, if you use other systems, just like ethylene, vinyl fluoride, vinyl acetate, CTFE, TFE, this is the reverse tendency which is observed. And if you start from 50% of VDF in the feed, you can see that you have about 20% or 15% of VDF in the system. So in this case, you are not going to get a real PVDF-like compound. And so you have to drive the good conditions there is also this kind of monomers we also prepare in the lab, on which we study the reactivity ratio, in which you have on one side, you have a better reactivity of this monomer, but on the other side, on the over window concentration, you have a higher reactivity of VDF, this being called the azeotropic composition. And then the last family of comonomers is when at whatever the feed concentration of both comonomers, you are on the way to be about 50-50. In this case, this is alternating copolymer. So this is the case of hexafluoroacetone. Central Glass in Japan studied a lot of copolymers of hexafluoroacetone and VDF optical fibers. Hexafluoroisobutylene, this trifluoroacrylate, and this compound, which is more or less, I say, the cousin of acrylic acid. Acrylic acid homopolymerizes very well, but the presence of this CF3 here inhibits totally his homopolymerization. However, he copolymerizes very well with VDF. So now, of course, I'm speaking about a lot of literature search I've done, and also we worked on that. I think all my PhD students and postdocs work on that, because it was very interesting to figure out which comonomer was more reactive than the other one. And I give you an example. I give you an example of copolymers of VDF with fluoroacrylates. Just like alpha fluoroacrylates, difluoroacrylates, I call alpha beta or beta beta, or trifluoroacrylate, alpha beta beta, or trifluoromethyl acrylate. So you can see that you have different acrylates copolymerized in the same conditions. And indeed, when you do this reaction, this alpha fluoroacrylate is so reactive that it doesn't go to copolymers. He reacts on itself by making a homopolymerization. And then when you consume all, little, you can add some VDF. So we decided to soften his reactivity to make slowing by adding a fluorine here. So we synthesize, of course, by organic chemistry. And in this case, we have some statistical polymerization. So this was possible to tune the good conditions in order to have a good PVDF, let's say with 10% or 5% of this, in order to satisfy some properties. And this was the same in the case of what is called the beta-beta, exactly statistical copolymerization, and alpha-beta-beta gives some alternating copolymers, as well as this, what is called, this compound is called MAF, and I want to thank Tozo company because they supply this for us. So just to, how can we prepare this, let's say, this alpha-beta compound? So first, of course, we look at the literature. So it was very complicated in 7 steps by Jakubowicz, starting from trifluoroethylene, which is very expensive, bromination, then dehydrobromination, making a double bonds and chemical modification. Again here, making some esterification and having here this compound hydrolysis, making this alpha-beta difluoroacrylates. So very complicated. It was long time ago, more than about 60 years ago. Here, then Soviet in Paris made a similar reaction in 5 steps, but it was very complicated, starting from expensive trifluoroethylene. But we decided to go another way. We started from difluoroethylene, radical addition of methanol, in order to have this alcohol, then to oxidize this CH2OH to make the carboxylic acid, and then by dechlorination in zinc to prepare this alpha-beta. So this was good, and we decided to have a patent on that, CNRS patent, and this was also more interesting that this monomer could copolymerize with VDF. So Dr. Ruguillo did a very good job in this way, as much as in organic chemistry than in copolymers. And this is the NMR. So for us, you understand that in order to show this diagram of composition, it's very important to well identify and to calculate the concentration, the composition of a copolymer. How much VDF we have, how much alpha-beta difluoroacrylate we have. And indeed, when we see this nice signal at -92, this is assigned to VDF units in a row, which is called the head to tail, while in the case of what is called the dyad VDF adjacent to our alpha-beta compound, we have a system here. So we have a shift on the signal. The CF here, the beta and delta are linked to the two fluorine of the system. And so from the integral of the characteristic signals, it was possible to calculate the content of VDF. So in this case, we have 65% VDF here. This is, sorry, in the copolymer. So this was very interesting. And these are the two reverse addition. This is the head-to-head addition. You know, in PVDF, indeed, you have this kind of structure, which is, let's say, 92, 95%. And then you have the reverse addition. So this is a head-to-head, but also then you have tail-to-tail. So CH2 is adjacent to CH2. And these effects are very important because they can make a difference, especially in the thermal stability. So this is an example how we have been able to figure out the structure of this diagram of composition. And as you can see, we monitor variation by proton and fluorine NMR. So of course, with fluorine, with proton NMR, we are able to see the CH2 coming from VDF and also the CH coming from the difluoroacrylate. So just an example here, fluorine NMR, I don't show the proton NMR, but this is the calculation, and by different techniques of calculation, Feynman-Rose, Killen-2 dose, extended Killen-2 dose, it was possible to have an idea of the reactivity ratio. And indeed, we are not very far from a kind of ideal copolymerization in this case. So this statistic, okay, the other one was prepared by CCl3 plus VDF, led to a monoadduct. This is a chain transfer agent. I will speak on Monday on thermalization. And indeed, this monoadduct can be oxidized in presence of oleum to make the acid moiety, and then the hydrobrominated. Or you can have also the ester product by oleum and then followed by methanol in order to have the ester group and then the hydrobromination. And then we could do also the nice NMR fluorine NMR spectrum, showing that we have indeed, when you have a macroradical terminated by VDF, you can have a chance to react onto the less hindered side, CF2, but it's a little bit big because the fluorine atoms are bigger than that of proton, or let's say the more hindered side here. And we have found that A prime and B prime are here, and A and B are here. You can see the little star I put here with a very nice system as because of the presence of asymmetric carbon here. So the two fluorine are non-equivalent as well as these two fluorine. So we have been able to prepare also this kind of, this is the Petrova's PhD. It was 20 years ago, 25 years ago. And by addition of ICL onto CTFE, we could prepare some intermediate that require some organic chemistry in order to have a trifluorovinyl hydroxy, trifluorovinyl silane, trifluorovinyl sulfur containing carboxylic acid or alcohol, acetoxy here, epoxide, and a diene. So she made various monomers that we copolymerize with VDF. Also, collaboration with Professor Chad Friesen in the Canada. He came for sabbatical, and Chad told me, "Oh, we have prepared some oligomers containing some trifluorovanillin group. Wow, this is very interesting because we can copolymerize with VDF." And this is what we did. It didn't have so much amount, about 8 to 10 grams. So we decided to make about Carius tubes with 1 gram of VDF and let's say 100 or 200 milligrams of compounds here, because this is heavy. This is 64 molecular weight, so this was gold for us. And we used either persistent radical releasing a CF3 or some peroxides, just like peroxypidalate, in order to make some new VDF containing perfluoropolymer side groups. It's a kind of graft copolymer in which we have a linear backbone made of PVDF and some side groups bearing some perfluoropolyethers. So by NMR, of course, because these were not possible to inject by size exclusion chromatography, it was possible to measure the molecular weight by VN group, because VN group was in the presence of this PPFR was a CF3. And in this case, we have a nice label, as I showed in the beginning, of the signals at -61 ppm on 3 nanometer, and knowing all the signals of the monomer and of VDF, it was possible both to determine the content of VDF, the content of perfluoropolyether, and the molecular weight. So we had molecular weights ranging between 25 to 77,000 gram per mole, with a TG ranging between -79 to -54, which was exceptional. I have to say, don't forget that the TG of PVDF is -40. And by adding some side groups, usually you increase the TG, but because of the presence of very low TG, which is about -100, -120, it was possible to have very, very low molecular weight with a very high thermostability. Because you can say, okay, you make low molecular weight, but if we make low molecular weight, we couldn't get so high thermostability because you have some evaporation usually when you heat it up. But even up to about 500 degrees Celsius under air, this was exceptional. So this is at the beginning of a reaction, and this is at the end of a reaction. So this milky product, indeed, was this copolymer swollen by the solvent. But today I would like to focus on one monomer, which is very interesting. I mentioned that MAF is reacting very well with VDF, and this was prepared by bromination of trifluoropropene, followed by dehydrobromination. And then this reaction of acidification of bromine into carboxylic acid could be done first in Professor Ojima in New York, and then it was scaled in Tozo company in the presence of carbon monoxide and a palladium salt. So this is a very expensive reaction, very dangerous, and this enables to use for making uracil. The first presentation I made today was 380 uracil for ophthalmology, and this company uses this monomer to make, in the presence of urea, to make some uracil. But when I met some researchers in conference from Tozo, I say, could you please send me some sample, because we would like to make some tests. And indeed, when you look at the literature, Professor Narita in Omiya in Japan made a lot of anionic polymerization. And it works because you have two electrowithdrawing groups. CF3 is electrowithdrawing, VSTL is electrowithdrawing, so this can be done by anionic polymerization. However, in radical polymerization, you make oligomers with very low DPN. So Ito makes some work, Macaro, they didn't evidence that they could supply some radical polymers with high molecular weight. But because it's electrowithdrawing, it can react with electrodonating comonomers, just like vinyl ethers, alpha olefins, or norbornene. And Hiroshi Ito in IBM, Aglieto in Italy, or even we did some work of copolymerization with vinyl ethers, and it was successful to show that it was alternating copolymers. Indeed, with VDF, the situation was very interesting, and my PhD student so 25 years ago started some work on that and showed that we have a tendency to alternating. When you look at this diagram of composition between, let's say, 20% and 75%, it's almost 50%. This is great. And even it was possible to make therpolymers, VDF, HFP, and MAF, in order to prepare this kind of Viton carboxylic acid compound. And the evidence of alternating copolymers was the low reactivity ratio. Usually when you make the product of the two reactivity ratio, you have to go to a tendency of 0. Of course, there is 0 here, but with so low reactivity ratio, we ensure that we have a trend to alternates. So we decided to work and to modify this math. So Sanjeev, you have some memories, and to put some phosphonate, to put some furane, some cyclocarbonate, some allyl compound, or some freenated ether, because there was behind that, there was an idea for anti-corrosion coating, because the phosphorus is very important, especially phosphonic acid can adhere on steel and enable some anti-corrosion, and also metal extraction. Self-healing polymers, so we published with Professor Banerjee a very nice paper in polymer chemistry here, and also here. Cyclocarbonate was for solid polymer electrolyte, and as well as this furinated ether, and this was also for hydrosilation. And of course, I want to thank Tozo because they supply us with this MAF compound, which was very important. So the first action was the use of synthesis of this monomer. So it was possible to use dimethyl phosphate with formaldehyde to make this primary alcohol, and then the acid chloride could react, condense with this primary alcohol to lead that. It was good. And then this was copolymerized with EDF in order to prepare some PVDF containing phosphorus. And this was the PhD thesis of Mohammad Wabi. And Mohammad, at the beginning of his PhD, was helped by Professor Sanjeev Banerjee, that I would like to thank again for his very good job. So this was hydrolyzed into phosphonic acid and used as additive in photopolymerizable coatings from two diacrylates. You know, when you make diacrylates polymerization, you have a cross-linked material because it's what is called telecalic, and the mixture was added with a photoinitiator spread on a steel, not stainless, it was a steel, and then photopolymerized to see how the coating was stable or not, and then put in a special machine for salination, because this simulates the marine atmosphere in very high salt concentration, sodium chlorine concentration. So the plaques were immersed, so there was a mist of sodium chloride, and then after reaction, we observe the state of the different plaques. So this steel was not coated, and after 1 hour it was corroded, so the rest was here. And as you can see here, the different plates coated with this formulation were very stable and could ensure a good anti-corrosion property. So this was because of the presence of phosphorus, and because, of course, the presence of PVDF, meaning that the phosphonic acid enabled to have a good adhesion on the steel, while the PVDF a good protection against the moisture. So the other idea was to take some cyclocarbonate, okay, and this cyclocarbonate was again prepared by condensation of this system, the alcohol with acid chloride, and the copolymerization led to different compounds. Hello? Okay. So cyclocarbonate can be opened by adding. Yes? Hello? The nucleophilic reaction of amino onto the cyclocarbonate, this is now the new generation of polyurethane, is made this urethane link with a secondary alcohol or primary alcohol, enables to have a very stable urethane link. And it was possible to make, by adding this tritosilane, to make some hydrolysis and condensation. First hydrolysis under low pH, because one of the drawbacks of PVDF is the sensitivity to basic, and then to allow the condensation by heating, casting, and making a film also onto some steel plaques. So you have here a system in which you make a coating directly on the plaques, and what we observe, these copolymers could be very efficient in with a scratch test. Okay, you make a scratch, and then with a test with Scotch tape, you try to remove the square that you have built with a scalpel. And in this case, you have a mark 5/5, which is the maximum, very good adhesion. But when you use PVDF, unfortunately, I mean, as expected, you don't have any groups enable the adhesion, and so you have delamination of the coating. So whatever you have cyclocarbonate or this system which undergo some sol-gel reaction, you have been able to add very good adhesion, and this was also evidenced by the presence of silane by IR. But we say, why not to use this sample to in order to make some electrolytes for lithium-ion batteries? And this was a collaboration with Professor Jean-François Gouhy in Belgium. Just to remind you that lithium-ion battery is a storage system in which the lithium are going to change from one anode to one another in the charge, and in the discharge, they go to the other side. They can pass through a separator, and they generate current. Okay. But sometimes,
sir,
yes,
we have 5 more minutes for this session.
Okay, that's good. I finish. So the issue is that you can have a lithium bridge between the two electrodes, a lithium solid, which make a short circuit and induce very severe drawbacks. And in order to avoid that, it's necessary to have some solid polymer electrolyte and to have very good adhesion between the electrodes. So when we look at my colleagues, Jean-François Gouhy, professor at University of Louvain in Belgium, use perchlorate, lithium perchlorate in the system and show that you have different structure. Of course, it's a semi-crystalline polymer because of the presence of PVDF units, but it's also elastomeric. And when you look at the conductivity, so versus the temperature, so this is 80 Celsius, okay? You have a conductivity which is higher than 10⁻³ Siemens per centimeter, which is a challenge to reach higher than this. Now, the best are about 2 or 3 10⁻³. So we are in a good point in this way. And what is also very interesting is the good electrochemical stability at high potential. Usually now the tendency is to be stable at 5 potential. But you see at 5 potential, we have just a slight oxidation. If you go to higher, of course, the oxidation is much higher. And we wanted to understand what's going on here. So we say, okay, maybe we can design a specific reaction in which we could understand what's happening. So we made a kinetics of radical copolymerization. And in this way, along the time, we measure the NMR spectrum. So, you know, we like a lot for in NMR. And we could see that a first unit based on alternating copolymer between MAF, cyclocarbonate, and VDF was prepared. So this is the unreacted MAF, which after 30 minutes is decreasing, and then this is stopping. And this stops more or less concomitant to another signal which appears, which is linked to the presence of PVDF. So what's happened is and you don't have any more. So this was amorphous in the first part. And then when we consume all the MAF cyclocarbonate, because we put about 10–15%, we had the next step polymerization of VDF in order to have a kind of diblock. It's a gradient copolymer in which you had the crystalline. So this could be understood by the different reactivity of all. So as you know, MAF does not homopolymerize, okay? So it cannot go through propagation, but you have a cross propagation. And here it was favored with a cross propagation again because of this alternance between MAF and VDF. And we measure, of course, the reactivity ratio. So you can see that they are very low. The product is about 10⁻⁵, so showing that it's alternating. And this strategy also was applied to some free native ethers, and we could have also reasonable conductivity. So I think I'm going to stop here and to show that this monomer is very interesting. And we published with Professor Banerjee a very nice book chapter by Ojima. He was very happy because Professor Ojima in New York started with a math and participate to the nice research, which is now commercially available. And with Professor Banerjee, we had a nice review chapter on among all the different syntheses and, of course, copolymerization. And so I'm going to stop because I'm waiting for questions. And it was a pleasure for you. Thank you for staying with me. And also for Professor Banerjee to invite me and to participate to this very nice job. Thank you very much.
Okay, thank you, Dr. Ameduri. The session is open now for questions. Students, if you have any question, you can ask now. Dr. Ameduri will be back with his lectures on November 20, that's Monday. So in case you want to come back on Monday and ask, that is also fine, or you can ask now. We'll wait for a few minutes. You can raise your hand in the team so that we got to know who wants to ask.
Saikat Banerjee wants to ask.
Wants to ask?
Yeah.
Okay, so Saikat, I think you raised your hand, so you can ask question.
Hello.
Yes.
So my question is actually, I am working actually with fluoroelastomers. So my question is in compounding of fluoroelastomers, how that means what is the normal mixing temperature in Brabender plastic order for compounding of fluoroelastomer? That means and pre-compounding and compounding. What is the normal temperature in Brabender mixing? And the second question is that to optimize the Scott safety and the cure characteristics. That means I have to obtain a optimum maximum torque. That means the state of cure and the Scott safety value should be optimized. So for that, actually, I have actually that mixed some way, the way like.
Hello.
Yes, sir. Yes, sir. Can you tell that what are the things I have to keep in my mind for optimization, both the things, and that previous my question, that two questions are there.
So for the first question, you asked me about the temperature of the Brabender for mixing your elastomer.
Yes.
Do you make any cross-linking agent in this or not?
Yes. In the pre-compounding stage, I have mixed the cross-linker as well as the phase transfer catalyst and the fluoroelastomer in the pre-compounding stage. Then the other compounding ingredients like calcium hydroxide, magnesium oxide, and the other compounding ingredients are added at a certain time.
So this means
this is the normal mixing procedure.
You have a pre-compounding, and then after this pre-compounding, you add a cross-linking agent. Can I?
No. Cross-linking agent actually first added with the phase transfer catalyst and the rubber in the pre-compounding stage, and the other compounding ingredients.
Okay, but it depends what is the cross-linking agent and at which temperature is able to allow the cross-linking. So could you give me more information on the cross-linking agent?
No, actually, I am working on this. Actually, this is confidential. Like the normal conventional cross-linking agents that are available already in literature, like bisphenol and the bisphenol A.
Bisphenol derivative. So you have to work at least at 80 or 100 Celsius, at least, to favor that. But I also maybe
80 or 100 degrees centigrade, maintaining that means the in cooling role, right? That chilled line, maintaining that. Controlling the temperature, right? 45 to 50 degree.
I think you have to look at which is the content of. You have some VDF in the elastomer, or it's
yes. VDF is in the elastomer. That means the tar polymer.
So what happens is you are going to get a reaction of the phenate O minus onto VDF.
Actually, when I get when I get maximum torque, then the Scott safety is quite poor. That means the TH2 value is poor. But I have to optimize the maximum torque that means the state of cure, mH minus ml value, as well as the Scott safety value, that means TH2 and TC90. So what is the normal procedures I have to follow?
I think that you have to check the literature on this using the phenate and this elastomers.
Yes, I have already studied your journal also. Your research paper also is there on this. I have already studied, but there is no specific thing actually about on this. This is not written in specific literature.
We published a review paper in 2005 on cross-linking of VDF containing fluoroelastomers.
Yes, that one I have already studied.
Look at this paper because you have a lot of information on the use of the different cross-linking agent and also how the temperature, the mechanism, and also I advise you to check the papers from Walt Schmigel. He was working for DuPont for 30 years. And his specificity is on curing elastomers. Walt Schmigel.
Schmigel, right?
Pardon?
Can you repeat the name once again?
Schmigel.
Schmigel. Okay. Schmigel.
Yeah. So if I can come in, so let's be precise to the content of the course. I think the question Shaikat is asking is relevant to his research because you need to understand this session and everything is recorded. So research related question we will try to avoid. You can simply send an email to Dr. Ameduri and have a meeting. That will be better, I think, because this recordings and everything will by default go to the Ministry of Education and it is being live streamed.
Okay.
So that's the request from my end. If there are any further query, you can ask for specific query related to fluoropolymer research or something. You can contact Bruno via email, I think. But for this course, you try to stick to the content. Yeah. So we will be able to take one more question because of the paucity of time, and then Bruno will be back on Monday for the next series of lecture by him. If there are any questions, please raise your hand, or else we'll be closing the session. Okay, so I don't see any more hands. So okay, so I'll take the opportunity to thank you, Bruno, for your nice lectures and the session, and we'll be happy to welcome you on November 20 at 3:30 p.m. IST for the next session. Tomorrow and day after tomorrow, I will be taking the lectures. Yeah, thank you, Bruno. See you on Monday.
Okay, thank you very much, Sanjeev, for organizing this. Okay, I appreciate. Okay, bye-bye.
Yeah. Thank you. Bye.
Thank
So we'll close the session. Thank you.
See you on